Okay, in this video, we're going to be looking at confidence intervals for populations and means. Okay, so if you could just see on the right hand side there, you can see this full cream milk and stuff like that. Have you ever wondered where they come up with these numbers? I guess these are average numbers, right? And you'll see them on lots of containers. The reality is we don't really know what the mean is of the population a lot of the time. However, we can create these formulas where what we do is we create an interval. Um, where were we there? So we create an interval. So it might go from here to here. Okay, so there's some value at this side and this side, but we think, and with 95% confidence, that the mean will be somewhere within this interval. Okay, so they call it a confidence interval, and we can be 95% confident. We could be 85% confident. We can choose the confidence interval, but we can actually get an interval where we believe the mean will be. All right. Now, there's a bit of formula work to explain it, and it does say it down here how the confidence interval is formed. And I guess to quickly explain it, the reality is, as you can see in this diagram, we use our standardized normal distribution where the mean is 0 and the standard deviation is 1. And so if you think of it that way, you'd have, if you want to work out where 95% would be, you could do an inverse norm. Okay, you do your tail to the right, and hopefully you can see here, there we go, and you'd have an area of 0.025, and you put your mean of 0 and your standard deviation of 1, and you get a z value of equal to 1.96. And so you'll see in a formula below, there's a value of 1.96. So we know that we would get 95% of the values, and hopefully you understand what z's mean, if you went 1.96 standard deviations above, okay, or 1.96 standard deviations below. Now what we've got here is a formula. So this shows us how to create the confidence interval formula. But basically what they're saying here is, we could talk about Coke cans again, maybe a 24 pack. If you took a sample, okay, let's say the sample is 24, so you can put it in here. We can use the Z formula here. So remember, the Z formula is the actual value for the sample. Take the real mean divided by the standard deviation. Now remember, this would be the standard deviation for this guy here, okay? So what we actually do is we can rearrange that formula. Now, unfortunately, there's a bit of an error in this formula. I'll show you where it is. But if you rearrange it, so this, multiply both sides by the standard deviation, and then if you subtract the mean out, this is actually what should be here. So just, can you change your notes, guys? All right. And we should have the proper mean inside. All right, so what this formula does is creates an interval. So if you can see in the middle, we should have our mean. So the true mean basically lies between a sample mean. So remember, could be like a sample of 24 plus 1.96 lots of the standard deviation. So remember, the standard deviation in this case for this guy, that would be 24 down there, wouldn't it? But that was the formula we've used before. And on this side, it would be the sample mean, subtract 1.96 standard deviations below. All right. So when you put some numbers in there, what you create is basically a line, an interval. What also is important is the sample mean is in the middle. Okay. And then what we're doing from that sample mean is we're adding 1.96 lots of the standard deviation, and you'll get to this point here. And if you subtract from the sample mean 1.96 standard deviations over n, you'll get to this point here. And so, like I said, we'll be 95% confident the true mean is somewhere in there. Okay, we're not exactly sure where it is, but we can say with 95% confidence it's in there. All right, so apology about that. So just check your formula. It should be the sample mean there. And remember, what's the sample mean? Well, it's a bit like those guys we've already done, samples. X bar n. All right, so in this case too, so the formula is incorrect here as well, right? So the formula should have the sample mean there, should have the sample mean here as well. So the true mean, there it is, lies within that interval. So like I said, we've got these intervals. You can see what they've got on the right-hand side here is a population. Okay, so that this is the true population, this big normal here. And so what someone's done is they've taken some samples. Now, these are not like X bar n's. This is just like one sample. And, they've done one sample and created this interval. They've taken another sample, created the interval. What you actually know, you can see one interval, there's X1. There we go. It's there from there. Another interval is here to here. And another interval is here to here. But what's interesting, I'll just do it in a different color. You see this sample, what did you notice about the interval it created? The true mean is actually at this point here. It's not in there, is it? All right. And that's actually really what's going to happen, because you need to realize that when you create these intervals, only 95% of the time it'll be correct. All right. So even though we're creating this confidence, it's still not exact. Okay. So what I'm trying to say is, in 100 goes, if you did 100 of these intervals, you would find 95 of them will have the true mean in it, and 5, well, on average 5, would not. So here's an example of one of those 5 out of each 100. Okay, so we need to answer this question below here. So it says, what do you notice about X4? So we can just say true mean does not lie in interval as 95% confidence interval does not contain does not contain mean all the time, true mean all the time. All right. Yeah, so you just need to realize that's what 95% means. Okay, so we see this formula. This one's written correctly here. So in general, all right, the true mean will be within the sample mean take z value of the standard deviation, or the true mean plus the z value. When it's a 95% confidence interval, the z value is 1.96. Okay, so you'd have a 1.96 here. This little activity here just quickly tells us how to work it out for any other confidence interval. We could do an 80%er, we could do a 96%er. A lot of you might think, well, why don't we do a 99% or a 100%er? And we'll sort of explain that a bit later, why that's not possible. It's actually becomes really hard to make that confidence interval larger. So how do we do that? It's actually not that hard at all. I mean, I guess we talked about it before, but I think just doing an example might be good. You've got your information here, but we'll just do it in a quick example. So if you want to do a 90% confidence interval, okay, if you look at your distribution, we'd be going, well, we want this area to be 90. So what we do is we think about this area, and this area would really be 1 take our confidence interval as a decimal divided by 2. And you can see that's that area there. There it is. So that's the area you want to focus on. And we actually want to find this K value, or in this case, a Z value. So if you just do a tail to the right, okay, there's the tail to the right, guys. All right, the area under the curve, and you can see it's really 1 take the confidence interval as a decimal, just like I've got there, over 2. So in this case here, it'd be 0.05. Okay, and then you enter the mean and the standard deviation as 1 and 0. You get your Z value here. So the Z value in this case would be 1.64. So if you wanted to write that down, the confidence interval, I'll just run out of space here. We could put it up here where the formula is. So in this case, the true mean would be, from the sample mean, we would add 1.64 lots of the standard deviation. And the lower interval would be the sample mean take 1.64 lots of the standard deviation below. Okay, those signs can also be equals. All right, even though you can't equal a value in these continuous variables, it's okay to write that. Now here's the calculator instructions for it. So I guess I've got to admit my calculator's not working on my computer, so we'll just have a quick look at these and you can just do them as you go along. So just got to realize it's not distribution here, it's interval. So when you're in the stats menu, just hit interval, okay, and then you hit Z, and then it's 1 sample, okay, and then you'll get your screen, and it's pretty obvious. You put your confidence interval in, you put the standard deviation that has to be given, actually. I haven't explained that yet. You put your sample mean in, and you need the number in the sample, okay. That's all those values put there. So we've got an example here, and what we'll do is do this one by hand, and then we'll do one with a calculator on the side. All right. So we've got a sample of 60 yabbies. So, it's a bit like going x60 here, right? Okay, but normally when we write these, we just write the sample mean down here. So the sample mean was 84.6. We know that there are 60 yabbies, all right, and they want us to find a 95% confidence interval. We do need the population standard deviation, okay? I'm not exactly sure how they do it. I think statistically it's very close to samples, so that's how they derive it. Anyway, our formula would be the sample mean. So we know that the true mean lies between the sample mean plus, if it's going to be a 95%, it's going to be 1.96 times the population standard deviation divided by the square root of n, or it's going to be the sample mean subtract 1.96 lots of the standard deviation divided by the root n. All right. And if you put all that in and calculate it, you'll get this to 3 sig figs. All right. So remember, this is a confidence interval. So if you read the question, it says, look, we've taken a sample of 60. We've discovered that the sample mean was 84.6. We can actually make a prediction for the population, which is pretty cool. So we actually think for the population of all the yabbies, we can be 95% confident that true mean lies in this interval. You don't need to write this. I think I'm just trying to write it to help you guys understand it. Right, so that's actually got some practical use, hasn't it? Okay, you're looking at surveying animals and things like that. We can actually get some statistics that about the true mean by doing that. All right, so the next one we'll just put in the calculator. So I suggest you get your calculator out and quickly have a go. I'll do it as well here. So we've got the fat content, just like that first picture. We're talking about fat and sugars and all that. But we know the fat content in grams of 30 randomly selected pasties. So that's our n value. And the sample average was 15.9. They want us to do a 95% confidence interval, and we know that the population standard deviation is 1.35 grams. So we're going to try and do a confidence interval. So on your calculator, we enter this as the sample mean. We enter the population standard deviation as 1.35. The n value is 30. And just quickly check it on your calculators too. You should get a value of 15.4, mean 15.6. All right. So the important thing to realize is we can be 95% confident that the true mean, or the true fat content mean, lies somewhere between 15.4 and 16.4 grams. Okay. All right. What happens if we change the sample size? So we've got a quick example here, and it talks about a few things. So we know that the true mean lies within this interval somewhere. And what they've done is just given us some values. So we know our sample mean is 10, so that's written here and here. And we know that we're doing, we've got a standard deviation of 2, so that goes here and here. So we know that the n value is written here and here. And it will be on a few pages later, what we actually call this thing here that we either add or we subtract, it's called the margin of error. So I hope you guys realize that if you increase the n, it's going to change the size of this margin of error. Okay, it's going to either make it bigger or smaller. So what we've got is just using the formula, we've changed n and we've just put it into this calculation, and it's given us these confidence intervals. Now, they might not make sense like that. Certainly when you're doing real questions, I do recommend you draw number lines with these. We've got some number lines underneath that shows these. Okay. Now, there's our sample mean. In actual fact, that should be written like that. Okay, so the sample mean was 10. And you should note that as we increase in n, it's pretty obvious, isn't it? What's happening to the width of the interval? Okay, it's becoming less and less. All right. One thing I hope, and maybe might be a good point to make now, you need to realize that the true mean isn't in the middle, guys. It's anywhere. Okay. The true mean could be here with 95% confidence, or here, we don't know, all right? But the formula tells us that the sample mean is in the middle, all right? And we'll talk about that again a bit later. So as n increases, the width will decrease. And so if we just go back to the formula just to help understand that, okay, I hope you can actually understand if you increase n, you're going to be dividing by a number that's getting bigger and bigger and bigger. So as that gets bigger, this thing that you add and you subtract gets smaller, okay? So if you're going to add and subtract something smaller, it's going to get the width. It's going to be less of width and the spread's going to decrease. So I have put that in here. So we'll put that in margin of error equals the z value times that. And that's the key, the n value, okay? So as n increases, I might just call it ME, margin of error decreases in this case. And it should make sense anyway too. If you actually increase the size of the sample, you're going to get much, much more confidence in actually finding the value, right? Okay, if you're going to survey, if there's 2,000 people in the population and you survey 1,000 of them, you're going to have a good chance of actually predicting the mean there, okay? And that's why it gets smaller as well. So here's that diagram I'm talking about, and this is really important. Many people miss this understanding here with the formula. So here's our interval. So the interval is actually from here to there, okay? So when we talk about this interval, the sample mean is actually in the middle of it, all right? Because from the sample mean, we then add this value, the z value times the standard deviation, and from that middle value, we then subtract that z value, okay? So the margin of error is basically this guy here, all right? So remember that. Where is the true mean in this interval? So the interval is from, you see there, it could be there, could be there, could be there. Who knows? We cannot actually get that information. All we can do is say we're 95% confident that the true mean is somewhere in there. Okay, when we talk about width of the interval, I hope you guys can see that now. If that's the margin of error, there's another one there. To calculate the width of the interval, it's really 2 times the margin of error. Okay, so it's 2 times z times standard deviation over root n. You can rearrange that formula to work out n. Okay, and that can be quite useful in doing some questions. Okay, because if you want to do a confidence interval, sometimes you want to work out how many people to survey. And so it can be quite useful. And you'll notice here it just says no. If the question wants the n value to be within an interval, you must round it up. And we'll talk about that when we do a question. All right. So let's have a go at some questions with regards to all this stuff. So in this example 4, you'll see that we want to do a 95%er. So we know we're going to have a z value of 1.96. We want to find the true mean. We can't do that, but we're going to find an interval. Oh, they've already given it. There we go. All right, so they've actually given us the answer to the interval. This estimate was based on a sample size of 60. Use this information to calculate the sample mean. Now, a lot of people will get stuck on this. I mean, I don't know if some of you will get it. You could look back at the image above, but I told you something is in the middle of this interval. So the bottom of this interval was 1 point. There it is there. Okay, the top of the interval was here. When using that formula, what is in the middle? Okay, it's the sample mean. Okay, because remember, you add the margin of error to get to this endpoint, and you subtract the margin of error to get to this point. So if you actually want to find the sample mean, guess what? How do you find the middle of 2 points? You take an average. All right, so if you just add those two quickly, and even though they look ridiculously complex, guess what? The sample mean is just 9. Yeah, so the sample mean is 9 there. Now they want us to find the standard deviation of the population. The population standard deviation, which was used to calculate it. So I guess using that formula, remember when we talk about our interval, we know that now that we know the sample mean, we can either pick the upper or the lower limit. Okay, why don't we talk about the what have I got? The lower limit, 8.5617. All right. So if I know that the sample mean was 9, and I know that the lower limit was there, remember this value that I subtract is the margin of error. So the difference between these two is the margin of error. So the difference between these two has to be the margin of error. Okay, we don't know that, but we know that the n value was 60. We know it's a 95% confidence interval. And like I said, to get to this point, we get the sample mean and we subtract 1.96 standard deviation of root n. All right, so obviously this is this value here. All right, so if you just rearrange that, I hope you don't mind, I'm just going to give you the answer here. The standard deviation is 1.732, I think. All right, it's doing that. So there's different. The problem with this formula is you've got to understand the formula, but there's many different ways they can ask questions. So you do need to understand the formula. You obviously need to use the calculator as well. So you've got to be careful with those types of questions. Okay, we've got a couple more examples here. So in these examples, it says we want the sample mean. There it is, of fat content of pasties, which has a population standard deviation. So there's our standard deviation of 1.35 to differ from the population mean by less than 0.3 grams. That is, we wish to find the sample size. So what they're actually trying to do here, to differ from the population mean by less than 0.3, okay, what they're trying to say is when we talk about our sample mean, we don't want it to be any smaller than 0.3 grams. So it means that we could go 0.3 grams this way. We don't want it to be any larger. Okay, so sorry, this would be from the sample mean, it could be larger by 0.3, or from the sample mean, it could be 0.3 less. So that is what differ no more than 0.3 means. All right. So I'm thinking about that question. We need to, and it says it before from here, no, sorry, below, it says here that the width will be 0.6. So can you see if we differ by 0.3, it means we could go 0.3 up or 0.3 down. And that really actually tells us the width. So if you add those two together, we know that the total width of the confidence interval can be 0.6. So you've got a formula on the previous page where to find n, okay, we actually just simply put 2 times the z value times the standard deviation over the width, okay? So the formula's on the previous page, but you put the width here, and it's just 2 times the z value times the standard deviation, all right? So that's going to give us approximately 77.79. But there was something around before. You need to round up. Most of you will probably do that. I'll explain why, okay? Remember n, if you increase n, what happens to your width? It gets smaller, okay? And it's really important to understand that when you do this question, we want it to be, it says, from the population mean by less than 0.3 grams. So there's two problems here. We need to make sure that we're either at that point or less. We can't go any bigger. And we need to realize that n is a discrete value, okay? So we can't have an answer of 77.79. So the question is, does it become 77 or 78? So I hope you guys understand that if you increase n, you'll make the width of the interval smaller, but you have to, because it can't be any bigger, all right? If you actually round it down to 77, you'd actually make your only slightly, but your interval is going to get slightly bigger. That's the opposite. And then it won't be less than 0.3 grams, all right? So it is said there, but yeah, it is a play on words there. So if it says no more or less, it has to be less than or equal to that width, you must round up. So the answer here is 78. I think that's supposed to go in there. All right. All right, some other things to talk about is the width, and it's quite interesting, okay? If you change the width, all right, what happens? So what we're going to do is just use that n formula, and if you just repeat this, so we've got a standard deviation of 34, so I'm just going to put that there. These are 95% confidence intervals, so they're 1.96, and we change the width each time, so we've got 5. So if we did it again here, it would be, again, the same, but we're changing the width to be 1. And in this case here, it'll be 2 times 1.96 times 34 over 0.1. So you can see here, gradually we're making the width smaller, which sounds good. If we could make the width smaller of our confidence interval, we could be more happier with our prediction, couldn't we? However, if you look at the n value, all right, n value there is 711. Look at the n value here. So this answer will be that. And look at the answer for this one. All right, so I did mention it earlier, like there's a lot of things where we think, wow, we could change these things and make it easier. The reality is if you want your confidence interval to be over a very small spread, it's actually bloody hard to survey that many people. You're not going to be surveying over 1 million people. You're probably only going to be able to survey them. All right. So we have to be using, there's a lot of common sense that has to be used when making confidence intervals. Because the reality is you just can't have them, really, really, really accurate. All right, so we've got an old exam paper question here, a long time ago. Confidence intervals haven't changed that much since then, to be honest. So we've got a car company. They've developed a new car. There's our sample. All right, N. Okay. We tested the car's fuel consumption. They found that the sample mean, there it is 9.8 litres per 100 kilometres. And the standard deviation is that. We're going to assume that's the population one. Let's calculate the 95% confidence interval. Now we'll just use technology here. So N is 100. The sample mean is 9.18. The standard deviation is 0.15. Okay. And your answer to 3 sig figs will be here to here. I haven't really mentioned it, but you can have an equal sign there or not. Okay. I haven't really explained it. Maybe you can just check with your teacher. Because it's continuous, you can't equal it. All right. So you can't have that, but in actual fact, it doesn't matter if it's there or not. Okay. So if you saw one of the earlier videos, you cannot equal a continuous variable. It's impossible, but it doesn't matter. All right, so they've got a claim here. So the company claims that the population mean is 9.2. All right. So what we have to do is go, okay, let's have a look at the claim that we created. So sometimes drawing interval lines can help. In this case, it's kind of quite obvious. So that's our interval from here to here. All right. So we could be 95% confident our true mean is in there somewhere. Where is it? I don't know. It could be there. Could be there. Could be anywhere. We do know one thing. What's in the middle? Okay. I'll pause. What's in the middle? The sample mean, because the formula is derived with the sample mean in the middle. All right. Now they're claiming that their fuel consumption is on average 9.2 litres. So let's have a look where that is. Okay. 9.2 litres is here. All right. So it could be true, couldn't it? So the company claims that the population mean is 9.2 litres. What features of this confidence interval make this company's claim believable? Okay. You just need to say what makes it believable. 92 lies within 95% confidence interval. Doesn't make it true though, but it does help their argument. Okay. If these questions are a bit strange, if they said it was 9.3, right, then we can go, you guys are lying. All right. So it's sort of hard to confer claims, but we can certainly call them out and say that they're false, okay? Because we just don't know where that true mean is. But we can just say that there is some claims that do sort of help with their story, I guess. All right, so we've got a different company produces a new computer chip for a car engine and makes the following claim. A new engine management chip will improve the fuel consumption of this car to this. Okay, so they're going to change it without changing the variation across the population. Okay, so what they're trying to say there is they're going to keep the standard deviation the same, and the standard deviation was 0.15. Okay, so that may have been missed by you guys. A consumer magazine decides to investigate. So what we're going to do is we're going to do another sample. So they've done a sample of cars and they've checked them out. And what they've found is that they've done a 95% confidence interval with a width of 0.16. They wanted to, that's right, they want to create the sample. Sorry, guys, I should read the question. Calculate the size of the sample they need to take. So they want to do a 95% confidence interval, but they want the width to be that. So they're actually going, you know what, for some reason, we think that our answer will be more accurate if we have a width of 0.16, okay? So calculate the size of the sample. So using that formula N, we just go 2 times 1.96, that's the Z value. Because it's 95, it's 1.96. We put the standard deviation, which you may have missed, okay, it hasn't changed from the previous, and then we put our width, okay. And the answer is 13.5, which would be 14 in the sample, okay. It doesn't, remember I said before about within, it isn't really clear here, but we'll just round up every time, okay, when in doubt. The consumer magazine chooses a sample of 15 cars, okay, that have been fitted with the new chip. It finds the mean is 8.28, so there is our X bar, and the standard deviation is 0.1 litres per 100. Calculate the approximate 95% confidence interval. All right, so let's just put them in our calculator. So we'll put this in, we'll put our standard deviation of 0.1 and the n value of 15, and we'll create a confidence interval as such. All right. Hence, comment on the claim that our new engine management chip will improve the consumption of the car. So if you're looking at 8.2, this one is one of those where I just said before, if you look at the interval, you can see it's outside, right? Okay. So if I was just quickly drawing that interval here, this is, so with 95% confidence interval, we can be 95% confident that the true mean is here, somewhere between here. So like I said, we can't really prove it exactly where it is, but there it is there. There's the claim, all right? So they're claiming that 8.2 is there. It's not in there, is it? All right. So we can be, with 95% confidence, we can be confident that this claim is not true. Okay, so our new management chip will improve fuel consumption to less than that. That's crap. Okay, so we just say a statement. So we say we can be 95% confident, can't be 100% confident that claim is not true. But we have to have a reason, okay? I guess the diagram's here, but we have to explain the diagram, okay? So we need to say as 8.2 litres lies below, okay? That's what you need to say, confidence interval. If you, it depends on the types of questions, okay? You've got to be careful. Lots of language here, but that will be exactly all you need to say. No good, because 8.2 is below. It's completely outside where the with 95% confidence where the true mean is. So hopefully you're starting to understand what confidence intervals are. If you look at this little joke here, it talks about the weather, okay, and the guy talks about the weather saying it's going to be somewhere between 40 and 200. He's almost, that's definitely a very good confidence interval, isn't it? Okay, so he's got a very large width there, and that will probably prove that the true mean is inside. Okay, you've got lots of these to do. They are very different. Okay, you've got lots of reading to do. All right, but I'm sure you'll be fine with them. Okay, so go to the orange book, and that ends this video.